Hey guys, it's Professor Floyd here, and I'm going to show you how to calculate the concentration of pentachlorophenol in a wastewater sample if we measure the headspace inside, say, a drum, or I think in the example I gave in my homeworks was a wastewater tank. So wastewater has been contaminated with pentachlorophenol. We pull a headspace sample and we find the concentration. So the concentration was found to be the concentration of the headspace 0.09 ppm. And we want to know the concentration in the aqueous phase. So we can do this using Henry's law. We've done quite a bit of Henry's law here of late, and I'm just going to real briefly give an introduction to what Henry's law is, and then we'll move on. So Henry's law is the idea that if you have a closed system, well, really it doesn't have to be a closed system, but if you have a stable system where there's a gas that is bouncing around inside that system, then of course gases move really fast. They're constantly in motion, and the majority of the time they don't realize, or they don't, not that they have people, but to personify them, they don't realize that there's anything else around. They're flying through free space until they collide with another molecule, and then they have an elastic collision. So this gas molecule will fly around, and he might strike, or she might strike the wall here and bounce off. And that's what causes gases to have pressure. Just like a balloon, you have gas molecules inside that balloon. The balloon doesn't just spontaneously collapse, it stays full. Even though it's pulling down on those gas molecules are exerting pressure back on the balloon, causing it to stretch out. So we have kinetic, and we have elastic collisions with our walls, but that gas is also striking our liquid surface. And when it strikes the liquid, sometimes it has an elastic collision and it bounces off almost just like it was bouncing off of the, say, steel wall of this tank or this drum. But sometimes that gas molecule strikes and it interacts with this really thick medium that we're calling water in this case. And so the water has a lot of molecular presence. And when that gas molecule, say it's oxygen, interacts with it, it participates in a little hydrogen bonding. And it coordinates with the positive side of water, with the hydrogen side of water where you have a partial positive charge. And now this molecule begins to diffuse in any given direction, including back to the surface. And so constantly you're having molecules strike the surface and start to participate in a diffusive migration through the water. When they stay close to the surface, they maybe come back to the surface. They reach their way back to the surface and then spontaneously leave the liquid phase. And this will continue to happen until, by diffusion, we make a uniform concentration of whatever this contaminant is inside our liquid. Liquid and air or gas phase. So we end up developing a dynamic equilibrium where the concentration or the mass flux is equal from the liquid phase into the gas phase and from the gas phase into the liquid phase. And so Henry's law is basically just describing what the ratio of the concentration is in the air to the concentration that's in the liquid. And so we express it in terms like this. The constant of Henry is equal to the concentration, in this case, our solvent is water, so the concentration of aqueous phase divided by the pressure. So pressure in the industrial hygiene environmental health world is oftentimes used as a stand-in for concentration, and vice versa. We take the vapor pressure of a particular solvent, and we use that as a worst case scenario for what a maximum exposure might be. Well, we take that vapor pressure, we convert it into parts per million, and then we evaluate it against health and safety standards. So this is a similar concept, except that pressure describes more the presence and the number of interactions that are occurring on that liquid surface. So it makes more sense, but really this is the same thing as saying the concentration in the aqueous phase divided by the concentration in the air or in the gas phase. So maybe gas would be the better way to note that. So we can of course isolate this and say that the concentration in the aqueous phase is going to be equal to the Henry's law constant multiplied by the pressure of whatever that gas is. So the pressure of the substance. So in this case, we have pentachlorophenol. Pentachlorophenol has a molecular weight of 266.3 grams per mole. And we can use the NIST web book to look up our Henry's law constant. So from NIST, we find that our KH equals 40,000, and then the units on this are moles per kilogram bar. Moles per kilogram bar. But it also tells us that there's another, so the NIST lists all the available data, and then might make some comments if there's inconsistencies in the data, but generally kind of leaves it up to you to decide which particular constant you want to use, or do you just want to average them all. And so it's a really great resource. Well, the other value they list is 11. So something just doesn't seem right that one value is 40,000, the other value is 11. They both supposedly have the same units. So when I saw that, I thought, no, this probably needs to be investigated a little bit further. So I got on Google, I did some web searching for Henry's constant for pentachlorophenol, and I found a really good resource in the National Toxicology Program. And that is going to be housed under the NIEHS and then under the NIH. But just look for it, just do a Google search and look for something that has NTP in the URL, and then go to that. So if you scroll down towards the bottom, they have other properties that are listed, and Henry's law constant is given by these guys, so by the NTP, as case of H, 2.45 times 10 to the minus 8. Minus 8, that doesn't seem right. It's completely backwards. It almost seems like it's the inverse. And it is atmospheres meters cubed per mole. So we can see we have moles per kilograms bar. So a volume, an amount of the solvent and the pressure of the material. Here we have the units are inversed. So because of that, that's why this one's 40,000 and this one's 10 to the minus 8, let alone our units aren't the same. They're inverted and they're not the same. So if we bring these to common units, let's just convert this into moles per kilogram bar. First, let's recognize that moles per kilogram bar, which is the way NIST likes to express it, can also be expressed as liters, because we're talking about solubility of water and the dissolvability in water. And so water's density is 1 kilogram per liter. So we can replace that kilogram with liter and know that we're not affecting things in any significant way. And then, right, so this is actually just moles per liter per bar. So if we take this, if we first start off by saying 1 over the constant that they provide is 2.45 times 10 to the minus 8, and then the units were atmospheres, cubic meters, bar, we can obviously just take this and put it into our numerator. So we have bar. So if we do that, now we're a little bit closer. And if we multiply by 1 atmosphere per 760 torr, and then we multiply by 1 cubic meter per 1,000 liters. Now we're expressing it in, wait a minute, what did I do there? I did something wrong. Atmospheres cubic meter per, oh, that's not bar. You guys have got to stop me when I do things that are wrong. Oh, this is mole. Mole. So I just copied my units wrong. So this is moles per liter torr. So we've got it in moles per liter bar. So we'll need to change it. Anyways, we're just trying to get them all in the same units. So this comes out to 53.7 moles per liter torr. And then our KH, the first one that was provided by NIST of the 4,000, is just going to be moles per liter bar times 1 bar per 750 torr. So 750.06 torr is 1 bar. And so if we take 40,000 and divide that by 750, we come out with 53.3. Same units, moles, liter, torr. So I'm guessing that this one is not the correct one, but the 53.7, 53.3 is correct. So I'm going to go with the NIST on this one of 40,000 moles per bar, or moles per kilogram bar, which is also the same thing as 53.3 moles liter torr. Okay, so that was actually the challenge to this particular question. Everything else about this question is pretty much trivial. It's just a matter of can you plug and chug. So our concentration in the aqueous phase is equal to the Henry's law constant multiplied by the pressure, and that's equal to simply plugging these things in, 53.3 moles. Now I'm looking for this in milligrams per liter, so there's going to be a little bit of unit conversion that we have to do, but that's just unit conversion. That's moles per liter torr multiplied by our pressure, and oh man, did I not calculate that yet? So our pressure, 0.09 ppm. Remember that ppm is a placeholder for times 10 to the minus 6. They're the same thing. They're interchangeable. ppm is not units. ppm is a numerical placeholder. So we have, it's just telling us we have 0.09 times 10 to the minus 6 fraction of something else is pentachlorophenol. In this case, that fraction is all the gas that's around. 0.09 times 10 to the minus 6 of it is pentachlorophenol. So how much is present in the first place? The total is 760 torr. And so we just do 0.09 e to the minus 6 times 760. And so that tells us that we have 6.84 times 10 to the minus 5 torr. Alright, so not a whole lot of pressure here. 6.84 times 10 to the minus 5 obviously that cancels, we're left in moles per liter. But we don't want moles per liter, we want milligrams per liter. So moles, we get out of moles by using our molecular weight. So 266.3 grams per mole. And then we get into milligrams by 1,000 milligrams per 1 gram. Grams cancel, moles cancel, milligrams per liter. Alright, we punch this all in and we get 53.3 times 266.3 times 1,000. And express that in regular. We get about 970.8, so 971 milligrams per liter. So that is our answer, 971 milligrams per liter pentachlorophenol in water.